Hello students, welcome to Physics Bouquet. In this video, I am going to discuss about Hamiltonian stationary state and energy eigenvalues. In previous video of quantum mechanics and its applications, I have already discussed time independent Schrödinger equation. And this Hamiltonian is related to that time independent Schrödinger equation. So let me write the time independent Schrödinger equation first. Let me write it in one-dimensional form. In one-dimensional form, I can write it as del square psi by del x square. Here it is function of x only, plus 2m by h cut square e minus vx psi x is equal to 0. This is function of x only. Here the potential energy is function of position only. This is one-dimensional form of the time independent Schrödinger equation. Time independent Schrödinger equation. In three-dimensional form, it can be written as, in three dimension, there will be three coordinates, three position coordinates, x, y, z, all the three will be involved. Therefore, there will write three-dimensional form as del grade square psi r plus 2m by h cut square e minus v. Here all the positions will be there, x, y, z all will be there, and psi r is equal to 0. This is three-dimensional form. Here it is representing del square psi by del x square plus del square psi by del y square plus del square psi by del z square. Since x, y, z, all the three coordinates are involved, here r is written. R is xi cap plus yj cap plus zk cap. Now, after a little bit manipulation, it can be written like this: h cut square by 2m grade square psi r plus e minus v psi r is equal to 0. I multiplied throughout by h cut square by 2m. That's why it cancelled out. Or it can also be written as h cut square by 2m grade square psi r is equal to e minus v psi r. Here there will be a minus sign. Or it can be written as minus h cut square by 2m grade square psi r is equal to e psi r plus minus v psi r. Right? Now bring this v psi r towards the left hand side. It can be written as minus h cut square by 2m grade square psi r plus v psi r is equal to E psi r. It can also be written as minus h cut square by 2m grade square plus v. Outside I can write psi r is equal to E psi r. Now you look at the bracketed term that is in the square bracket. This is potential energy. Now come to here. Here you can recall that in operator, while reading operator, quantum operators, we have and momentum operator is minus ih cut del by del x if it is px. Momentum operator is given in this form. If I am write p, then minus ih cut, great. Since it is x coordinate there, it is x. But here all coordinates are involved, so I am writing grade. This operator. Then our p square will be minus h cut square grade square. Let me divide 2m both sides. Now you see, I have obtained minus h cut square by 2m grade square for operator p square by 2m. But what is p square by 2m? Kinetic energy. So this is kinetic energy operator. So this is kinetic and this represents kinetic energy operator. So this is kinetic energy and this is potential energy. So sum will give us the total energy. So this is represented by a letter H. This total bracketed term is represented by the letter H with a cap sign. H psi r is equal to E psi r. And what is H here? This H is nothing but our minus h cut grade square plus v. And this is known as Hamiltonian. That means it is total energy operator, total mechanical energy operator. That is sum of kinetic energy and potential energy. One more thing I can tell, that this time independent Schrödinger equation is a eigenvalue equation. You see, when H operator operates with the wave function which is independent of time, giving us an eigenvalue into the same wave function. So this is an eigenvalue equation, and this is the energy eigenvalue. Energy eigenvalue for a particular quantum state, it represents energy of that state. That means if I operate if I write h psi 1, then it will be E1 psi 1. If it is h psi 2, then it is E2 psi 2. That means this for quantum state psi 2, this is the energy eigenvalue. For quantum state psi 1, it is the energy eigenvalue. So time independent Schrödinger equation can also be written in the form of eigenvalue equation. And this is Hamiltonian. Hamiltonian is nothing but total energy operator. So this is about Hamiltonian. It has a lot of applications. आगे हम पढ़ेंगे. But we have to remember that Hamiltonian is equal to minus h cut square by 2m grade square plus v. Now come to stationary state. Here I am writing psi r. This quantum state is stationary state. Why it is called stationary state? It is also called steady state. This time independent Schrödinger equation is also known as stationary state Schrödinger equation or steady state Schrödinger equation. Why? Actually, sometimes we misinterpret as stationary state means the particle is motionless. That doesn't mean particle is motionless. It has some other meaning. I will tell later on. Let me explain. Suppose I find out the probability density. Probability density. Probability density. Probability density. Probability density rho is given by psi RT modulus square. But what is modulus square? It is a complex function. So I can write it as, since wave function is a complex function, I can write it as psi into psi star RT. But we know that psi RT is nothing but psi r exponential minus I et by h cut. This is position dependent part and this is time dependent part. While deriving time independent Schrödinger equation, I had used psi xt is equal to psi x into phi t. So in place of psi x there is psi r because it is involving all the coordinates, and phi t is given by this. So and when we take complex conjugate of this psi, we will obtain psi star r exponential I et by h cut. Because when complex conjugate is taken, it involves iota, therefore this sign will change, plus, and here psi ka complex conjugate psi star. So we will obtain this multiplied by this. It will give exponential 0, matlab 1. So product of these two becomes 1. So we get psi r psi star r complex conjugate, and this is nothing but our psi r square. So probability density of psi rt square is same as psi r square. That means here probability density is independent of time. Statistical distribution of position and momentum of the particle is independent of time. So stationary quantum state means that the probability density is independent of time. मतलब the statistical distribution of position and momentum of the particle does not depend on time. This is the meaning. It doesn't mean that the particle is motionless. It has no motion. It doesn't mean so. So this is stationary state. Since probability density is independent of time, it is stationary state. And the equation of Schrödinger, which is time independent Schrödinger equation, is called stationary state equation or steady state equation. And the energy eigenvalue here we have h psi is equal to E psi. Here E is the energy eigenvalue for a. So energy eigenvalue क्या है? First thing you remember that to obtain energy eigenvalue you must operate the wave function with the Hamiltonian operator. Stationary states function. If a wave function is operated with Hamiltonian, then the specific allowed energy for that operation, specific allowed energy that is obtained. Specific and allowed, both terms are important. Specific allowed energy level with which it is associated, that state is associated, is energy eigenvalue. So primary condition is it must be operated with Hamiltonian, and second is it is stationary state solution. So stationary state solution, when operated with Hamiltonian, a specific allowed energy for the quantum state is obtained, and that is nothing but energy eigenvalue. So this is about Hamiltonian, stationary state and energy eigenvalue. In this video this much only. नेक्स्ट वीडियो में और एक नया टॉपिक के साथ मिलेंगे. हैव ए गुड डे.